In this video, we are going to learn the fundamental concepts of Einstein's general relativity. This video is going to give you all the necessary ideas, thoughts, mathematical descriptions, and the concepts which makes up general relativity. Although the mathematical part of general theory is very complex and requires advanced mathematical techniques and tools to learn, however, the basic ideas and the concepts are very clear, simple. So I would be using very easy concept to make you understand about those areas. I would be using less amount of mathematics, less amount of equations, but more of the concept building part where I would be using graphs, pictures, illustrations so that the fundamental concepts are very clear. Note that we are not going to derive any tensor or any mathematical complications of relativity, but we are going to learn all the fundamental concepts so that the idea of general relativity is absolutely clear in front of you. My name is Shaunak and you are watching this video on Physics for Students. Welcome to my channel. Before we go ahead and learn the fundamental concepts, let us look into what are the topics that we are covering today. So first we are covering going back a little bit into special relativity and how it emerged to general relativity. What are the inertial and non-inertial frames of reference? What is the equivalence principle? What are the postulates of general relativity? What is the principle of general covariance? How we move from flat space to curved space? And how do we measure curvature in general relativity? What is the use and why do we need tensors at all? What is Einstein's field equations? The different tensors called the Ricci, metric and the stressenergymomentumtensor, and finally the geodesics. First of all, we will move from special relativity and see how the special relativity finally emerged into general relativity. Well, the time was 30th of June 1905 and on this day something great happened. So first what we find is that on this day the annus mirabilis, which is the Latin meaning of miracle year, are the 4 papers that Albert Einstein published in Annalen der Physik, which means Annals of Physics, which is a scientific journal. Now, these 4 papers were major contributions to the foundations of modern physics. They revolutionized science's understanding of the fundamental concepts of space, time, mass and energy. Because Einstein published these remarkable papers in a single year, that is 1905, it is called as the Annus Mirabilis or the miracle years. The first paper explained the photoelectric effect, of which Einstein was awarded the Nobel Prize. The second paper is called the Brownian motion, which led reluctant physicists to accept the existence of atoms. You can call it is basically a temperature of substance is proportional to the average kinetic energy. That is basically the formulation. The third paper, special relativity, is something that we are going to look into. And the fourth paper is called the mass energy equivalence, is a consequence of the theory of special relativity, developed the principle of mass energy equivalence and the famous E equals to mc square, which you can see on your screen at the bottom, which led to the discovery of atomic energy. These 4 papers, together with quantum mechanics and Einstein's later the theory of general relativity, which is a subject of today's discussion, are the foundations of physics. Okay, so first, before going into the fundamental concept, we need to understand the postulates of special relativity. Very simple. The first one says that the laws of physics are invariant in all inertial frames of reference, which means the frames obviously which doesn't accelerate. Note that the definitions which I have written in red are very important, so I marked it in red. The second is very simple. The speed of light in vacuum is the same for all observers regardless of the motion of the light or observer. So here is a kind of a photograph which shows a kind of a movement. This is particularly for inertial frames of reference. So what does that mean is that if we are using inertial frame of reference, then the initial Newton's law of force equals to mass time acceleration actually holds in inertial frame of reference. That is the laws of physics are invariant. That means it is not changing in frames of reference, obviously, which is not experiencing any kind of an acceleration. Now, if we rotate the frame of reference, the force becomes F prime, and it also holds for a rotating frame of reference as long as it is in inertial frame of reference. Now, I don't want to go into this, but I hope you all know what is a Galilean transformation, where the x prime is the transform coordinate. So once we look into the x, y, z and t, that is transformed into x prime, y prime, z prime and t prime, then after doing all the mathematical calculations, what we see and what we find is that the acceleration is the same in both the frames, which particularly defines the first postulate that the laws of physics are invariant in all inertial frames of reference. Now, why I am showing you this? This is important because once we move from inertial to non-inertial, then all these things actually change. One thing very important is that why it is called special theory, because it is very special and specific to only inertial frames of reference. That is why it is called special relativity. Okay, so once we move into what we call the non-inertial frames of reference, I have just given a kind of illustration on the right hand side. That means that it undergoes acceleration, and what it undergoes acceleration means something is pushing, so we call it as a fictitious force. And Newton's law works well with it. Now, when we move from the inertial to non-inertial frame of reference, Einstein thought that if we are moving at certain speed, maybe a little bit more than that, maybe a car or an airplane or anything, but we have not yet calculated the laws of physics taking the highest speed of a moving object. So what is the highest speed of a moving object? Is the speed of light. So Newton's law works well with everything except for an object moving close at the speed of light. Now here I would like to take a pause, and I would like to tell you that there is a common misnomer which I have seen among students as well as when we read through internet, that what are the limitations of special relativity, or what are the limitations of quantum mechanics, something like that. The fact is that there are no limitations. Now, this is a misnomer which I have seen among young people and many other people who are talking about. Now, there is no limitation actually in special relativity. The fact is that special relativity works well with inertial frames of reference. It confirms, time dilation, length contraction, all those things. But as far as the frame of reference in inertia is concerned, things work fine. Things are no different. That doesn't mean that it has got a limitation, and that is why we have to go in general theory. No, general theory is something different, which works well in non-inertial frame of reference, and special theory also works in an inertial frame of reference. So it is not anything which has got a limitation. It would have been a limitation when the scientific theory would have failed in inertial frame of reference also. So it is a request, let us not think that it has a limitation, but it works within its own frame of work. Now, this is something which I would like to quote, that when we moved into non-inertial frames, that is, things are experiencing acceleration. So I remember it was in a Swiss office in Bern, where Einstein recollects that suddenly a thought struck me. He recalled, if a man falls freely, he would not feel his weight. This simple thought experiment led me to the theory of gravity. We will soon see that. Okay, so the first one is the principle of equivalence. This is very fundamental and we need to understand what it is. So the principle of equivalence states that there is no physical difference between an accelerating frame of reference and one in gravitational field, right? They are almost indistinguishable, right? So the gravitational force as experienced locally while standing on a massive body is the same as pseudo force experienced by an observer in a non-inertial frame of reference, right? So again, I would like to repeat that there is no physical difference between an accelerating frame of reference, which is accelerating up or down, and one in the gravitational field. If the two frames are equivalent, then gravity can have special effects. So I would like to show you this photograph, a person which is standing on Earth, right? And somebody on the right hand side, that person or object is accelerating at a speed say g. Both of them are indistinguishable, provided, yes, obviously you are in a closed kind of a cabin where other things cannot be seen, no sound, etc. So when it is moving up, and you're standing on the ground, your feet or the experience would be something the same. So here is something I would like to show. Now, one thing you should be clear that equivalence principle is a fundamental law of physics, right? That states that gravitational and inertial forces are similar in nature. Now, in the Newtonian form, it asserts in effect that within a windowless laboratory freely falling in a uniform gravitational field, experimenters would be unaware that the laboratory is in a state of non-uniform motion. So all dynamical experiments yield the same result as it is. So here, as you can see, that here is an elevator, you can think of it, right? Or an elevator cabin from inside, and that you are isolated from the rest of the world. Now, if you pick an object and let it drop, it falls on the floor exactly the way you would expect given your experience on Earth, right? Now, one thing is that if you see this here, actually this blue one shows that this is a bending. So the light ray, if I will show it in the next part, that it actually bends. So this part is clear that principle of equivalence tells that gravitational and inertial forces are similar and often indistinguishable provided the given conditions. Now, I would like to tell you that this Newton's law, Newton's experience of the apple falling at his home at Woolsthorpe, and Einstein's revelation of the idea that gravitation and these things, no physical difference between accelerating frame of reference and in gravitational field, is what I called Einstein's Newton apple insight. Yeah, it is very, very important because this actually led to the new theory of gravity. Just as why the apple is falling, Newton could gather, and he discovered, or he started working on gravity. So here is something which I have taken on the right hand side. You can see the same experiment. I am taking it with a kind of a spaceship or something which is moving upwards. Here is a photon emitter, and just take a look on the extreme right hand side of your screen. This is the apparent path of a photon. So when it moves up, the path gets deflected. So this is what is called a Gedanken, or you would say that is a German word for thought experiment. So there is nothing called gravity. This is what we have found out. There is, nothing which is called a gravity. So what it is that is causing the light to bend, right? So there is nothing called gravity, and gravitational forces, gravitational and inertial forces are often indistinguishable. So what it is that is causing the light to bend? So it is this one, the space-time curvature. But hold on, we have not gone yet up to space-time curvature. I am saying that once the elevator is accelerating up, if we shine a path of photon, the light emitting, it will apparently bend. And this, if there is nothing called gravity, because earlier we have just seen that there is no physical difference between accelerating frame and one in gravitational field. The question rises, what actually causes the light to bend? And the answer is space-time curvature. So the fundamental concept number one which we are coming is the equivalence principle. I don't need to repeat, but this is the point number one, fundamental concept. Okay, now we come to the second fundamental concept, but before going that, what I would like to tell you is that what is actually a postulate? Hold on with me because this is important. So a postulate is sometimes called an axiom. It is a kind of a statement, I mean to say where everything is agreed upon to be correct. So here you can read what are the postulates and mathematical statements we assume to be true It is assumed to be true without any proof and don't need to prove the postulates. Why I am coming to this, I will tell you. Now, in 1905, you see Newton's axioms were replaced by Einstein. The Euclid's axiom has been augmented by a postulate on the space-time, which is taken by Isaac Newton. Even Isaac Newton's, we just saw that the postulates have been replaced in 1905 by Albert Einstein. Another paper of Albert Einstein and co-workers, which is called the EPR people, almost immediately contradicted Niels Bohr concerning the interpretation of quantum mechanics. So we see that postulates often and on gets changed. The hypothesis and then to axiom and to postulates. These things change. The axioms, they change based on this. Okay. Now, what are the postulates of general relativity? Why this is important? The first postulate is called the principle of general covariance. Often and on I have seen that people generally miss on this, but this is called the principle of general covariance. Okay. So what it says is that the laws of physics themselves should be independent of an observer's motion. Now, this is the challenge, and this is where the problem starts, that once we move from an inertial to a non-inertial frames of reference, the laws of physics are not the same. Anyway, we will look into that. So the second one is called the equivalence principle, which we have just read, that the gravitational acceleration is the same for all observers in a gravitational field. Okay. So we first go ahead, and this is this principle of covariance, which actually led to the formation of tensors. But we are not going to speak about tensors right now. We are going to understand, and this is the equivalence principle. Gravity is not a force, it is a geometry of space-time, which we will discover how it. So first is that we need to understand what is a covariance. Now, first of all, the word covariance is comprises of two words. One is co plus vary. So it means it should vary together. Okay, so if I take a straight line or an object like this, so when it changes in this direction, we assume that covariance means vary with something will also change in this direction. And this is called covariance. Now, if I take this object on the left hand side of the screen, it can vary up to this, and it can even go there and it might vanish. So it is also called a covariance. So covariance is basically to vary together with another variable, particularly in a way that may be predictive. Now, this is a very, very important fundamental concept, because the entire concept of generating tensors in general relativity is the postulate number one, that is the principle of general covariance. Here I have shown this can also be called a covariance, that is the height of the person increases and so does the weight. So it is co-varying with something. But just remember one more thing, that covariance is also a statistical tool, and it is used to determine relationship between the movements of two random variables. I'm not saying much into that. So when two stock markets or two stocks tend to move together, right, they are seen as having positive covariance. And when they move inversely, they are called negative covariance. So it is being used in kind of a financial sector. So once you see the term covary, you should not get surprised if there is something which is used in the financial sector. So let us not forget that also. Okay, now here is a general demonstration. What do I mean, or what general relativity means about principle of general covariance? So in physics, the principle of covariance emphasizes the formulation of physical laws using those physical quantities, the measurements which would observers in different frames could be unambiguously correlated. So here is a person, maybe he is throwing a ball, etc. This is just an event. Now he throws the ball over here, right? Now this same person is throwing the ball over here, right? The same person. But this XY frame of reference gets rotated this, right? But what happens is that this event and this event, the events will be measured in the same way in all frames of reference. So I mean to say, I'm not trying to showing a projectile and thereby calculate the projectile projection. But what I'm trying to show you is that if this XY axis, this person is into any kind of an event, anything which is happening. If I rotate the axis or there is a change in the event, that person will also measure the same. That is called what is called a principle of general covariance. Same thing, this person again throwing a ball and this person again throwing a ball, but in a much more extended axis. Now these are hypothetical. I mean to say they might be wrong, because in tensors we use this rotation and stretching, but when it is extended in axis also, the events will be measured in the same way. So what I'm trying to tell you is that the principle of general covariance means that there should be something which will vary with something, so that the measurements of the events or the laws of physics would be same. So here is a sphere. If we are measuring this red line, if the sphere get extended to an oblate spheroid, then this line would also extend. So as put, this one is a stretch. So as put by Einstein, that the general laws of nature must be expressed by identical equations relative to all other systems, whichever way they are moving. This was the basic challenge of Einstein. So mathematically, the physical quantities or the equation must transform covariantly, that is under a certain representation of the group transformation between admissible frames of reference of the physical theory. This is referred to as the covariance. I mean to say the general covariance. So this is something where the events are happening, the axes are rotated, flipped, stretched or whatever, but still we can understand the laws of nature, whichever the way it is moving. So the fundamental concept number 2 is the principle of general covariance. Let us take a pause and let us understand. So first was the equivalence principle, and then the second concept is the principle of general covariance. We have to devise something so that anything, any change which is happening, we can measure them. Okay, so now when we move from inertial to non-inertial frames of reference, we have to move from a flat space to a curved space, because general theory of relativity is all about curvatures. Okay, if I get a kind of a flat surface like this, for example, and I get a vector A, now the components of the vector in y direction is ay and in x direction is ax. You will soon be able to relate this example with the example of throwing the ball that I have shown. Now if this is the component of the vector marked in red. If I get into a curved surface, so I put this in xy and I get a kind of this kind of an x prime and y prime, right? And now I take the same vector A and I try to measure the component in the x direction, which is a prime x, and in y direction, which is a prime y. Now see what happens is that these are the lines which are joining. So a prime x, as you can see, is much longer than the flat one, and a prime y is also a little bit longer than the flat one, and a is invariant. That is, the vector doesn't change, right? The components of the vector are changing, but the vector is invariant. So in this frame of reference, which is a static frame of reference, you see I'm showing you another example, ax and ay. So these are the two. Now if I rotate that, earlier I have stretched, now I have rotated. So you see this a prime x is a little bit longer and bigger, whereas the extended a prime y is a little bit shorter. I'm going to say the components of the vectors now vary from a static frame of reference to a rotated frame of reference, right? But what is our objective? The principle of general covariance. That means that whatever it happens, we would be able to measure the laws of physics independently of whatever is happening out here, right? So in Newtonian mechanics, space, time and coordinates are independent. So if I get a kind of an axis like this, x, y, z is the space and time is t, then also we can form a kind of a tensor. And so this person is throwing or is going to this person. So here is a kind of a path, and each point, this one, this one, this one, each of these points are measurable. These are measurable, right? Whereas if we get a kind of a crazy curve like this, so we are moving from this, here also we are measuring the same x, y, z and time t, and these are the curvilinear coordinates, and this is the same person going or throwing a ball to that, and these are the points. So we get a curve like this, right? We get a curve like this. Now, most important is that you see, once we try to measure these are not orthogonal. That means these are not perpendicular. So it creates a problem. So the right-hand side equation actually shows that in a flat space-time, we can also form something kind of a tensor. And in the non-orthogonal plane, that carries a problem. So here also we can form a kind of a tensor. So this is why the manifolds and tangent bundle and tangent space, all those new terms and new mathematics come. Anyway, we are not covering into that. Come back to that later. So if we get a kind of a flat surface, we get a straight line like this, no problem. If we get a curved surface, we get something which moves like this. So if we take a kind of a linear algebra, we make a kind of a matrix 1, 2, 3 up to n. So the tensor basically gives that kind of a thing which is called a multi-dimensional array. Why? Because if you get a kind of a graph like this, so the base kind move this way or this way or this way, but the vector remains the same and the tensor also varies accordingly. So we are coming to the tensor part. What I'm trying to show you is that from a flat surface, once we move to a curved surface, the I would say the components of the vector changes, whereas the vector remains the same. How do we measure the changes? That is where the tensor comes into play. So if you get this kind of a form, x1, x2, y2, then we can use Pythagoras' formula just to call back this, right? We get a value. But however, we get a curve like this formula won't apply. Very true. The Pythagoras' theorem of flat space won't apply. And that is why we need tensor to define compute lengths of curves, infinitesimal distances, and tangent vectors. We don't have to worry about tangent vectors, we are not covering. Okay, so what is the fundamental concept number 3? That we are facing some problem in measurement of vectors because these are not orthogonals. So first we started with the principle of equivalence, then we moved into the next fundamental concept, and now we are on to the third one. We will revise those fundamental concepts again and we will put the picture together. Okay, so now as we have seen that there is some kind of a challenge that we are facing in terms of measuring the basis of vectors which are moving and creating all those kinds of problems. So that is why we need to understand why do we need tensors in general. Now the thing is that we need to create a mathematical model so that we can measure or predict the change of events. So either in the contravariant manner or in the covariant manner. So we will explain those terms, don't worry. So tensors will help us understanding the transformational properties like the rotation of the axis, the stretching of the axis, always the same in all coordinate system obviously, and whose components transform in a nice way. So this is the reason that we need to form a tensor. Okay, so if the vector changes, then there is a problem in measurement. The vector remains invariant, the components of the vector changes, and we develop a method or a tool to measure them, and any mathematical entity which is invariant, that means doesn't change under rotation or coordinate system, is called a tensor. So you can just take a note of those that why do we need tensor. But there is something which is called a covariance. You have already ordered that the principle of general covariance. This actually leads to something which is called covariant tensor. That means it changes in the same way. So if we get a vector like V, and if the line is moving, say for example in this direction, right? So vector V is moving in this direction, the covariant vector or the covariant tensor, the change will be also in the same direction. Whereas if I take another kind of a tensor which is called contravariance, that means it will change in the opposite, the contravariant vectors or the contravariant tensors. So if you take a vector V which is moving in this direction, the next vector will be bigger than this, right? It changes in the opposite direction. So don't worry, we are not going to talk about those indices and what is contra and covariant vectors. It is there in my playlist separately in tensors. and general relativity also. But I mean to say that a covariant tensor actually changes in the same way and contravariant changes in the opposite direction. That is why we need physics or a system where everything is covariant. That is, it is changing in the same way, predictable way, easier for us to do mathematics. So here the distance vector is doubled. So that is why it is called contravariant. It behaves in the opposite manner. Okay, so why do we need tensors? So if we get this kind of a graph, right, and these are the masses, I mean to say these are mass. So you see that the mass causes a dent in the space-time, which we are going to come. So these simple presence of mass causes the space-time to distort, right? Small mass in a small way, bigger mass in a bigger way. So tensor equations retain their form. So when it is changing, it will retain the form as we change the coordinates, which is the whole point of GR. And in GR, tensor obeys the rules of diffeomorphism. You can ignore the second point. Tensors, because of their transformational properties, are essential in writing GR, and it is coordinate system independent. And you can just think of space-time as a material undergoing stress, strain, and tensors describe the way the material deform, that is the stress and strain. This is, I hope, is clear that why do we need tensors? Because we need to retain the change that is happening, and that is the whole point of getting a system which varies in a nice predictable manner. Okay, here is something which I repeat in almost all of my lectures. So just don't imagine tensors as they are not generalization of vectors or matrices. Now, before coming to this ice cream photograph, what I'm trying to tell you is that tensors are not generalizations of vectors in any way. It is slightly more understandable to say that tensors are generalizations of matrices. In the same way that it is slightly more accurate to say vanilla ice cream is a generalization of chocolate ice cream than it is to say that vanilla ice cream is a generalization of dessert. Closer, but still false. So vanilla and chocolate are both ice creams, but chocolate ice cream is not a type of vanilla ice cream, and dessert certainly isn't a type of a vanilla ice cream. So please, I beg to all of you that you don't confuse, do not compare them to vectors as you learn, because do not compare them to matrices also. So what we call the technically vectors are generalizations of tensors. The problem comes, which is it is a kind of a linear matrix. So the array of number which it comes here, and from there we make this kind of a matrix, and then we immediately get into a kind of a what we called a tensor, right? So that is the reason that we try to tell the tensors are generalizations of matrices or matrices. No, it's a kind of linear map which I have already discussed in my earlier video. This is kind of a note that we should not forget and misinterpret tensors as generalization of vectors. We come back to the topic. So it can be defined as an algebraic object of multi-dimensional array, mathematical object that can be used to describe physical properties, and in simplest form it is the quantity having magnitude, direction, and a plane. So magnitude and direction we already know is being covered by vectors, while plane is called tensor quantities. So fundamental concept number 4 is we need tensors in general relativity because for the basic postulate. Why? Because the basic postulate tells that a system should be covariant. So we need a system or a mathematical tool that should covary, and tensors help in that. And number 2, there's a way of measurement where all the laws of physics are the same. The stretching, the rotation, whatever it happens, the laws of physics are the same. So now you see we are slowly moving one by one, step by step in the fundamental concepts. I hope you are enjoying this, and you can always subscribe to my channel and click on the bell icon to get further notifications. So far so good. So we now come that how do we understood that we need tensors, but how do we measure curvature in general relativity? I mean to say, how do we measure that? A nice analogy is that we have the planet Jupiter, Earth and Mercury. We all know that Jupiter, being the heaviest and the biggest planet, has got a more dent, has got a more curvature. So it is, you can see this, I would say the weight and the gravitational acceleration is this. Earth, we know that it is less heavier than Jupiter, so the curvature, as you can see, is less, and that is why the weight and the g varies. And Mercury, being the smallest, it has got a very less curvature compared to Jupiter and Earth, and that is why you can see the weight. So in this way, I mean to say, we can astronomically, the curvature actually causes the dent, and it affects ultimately the g and the weight of that particular object. So tensors measure the curvature. Okay, so we come to what is called the Einstein field equation, which actually is the ingredient of GR. So this is the Einstein equation, and it comprises of 1. A Ricci curvature tensor, 2. A metric tensor, 3. The Riemann curvature tensor, and 4th is the stressenergymomentumtensor. So I request the viewers to let know that we are covering the first, second, and the fourth one, but not the third one, because it will require more mathematical understanding, which is out of the scope of this video, because we are just covering the fundamental concepts. Okay, so let's see what these elements are. So Ricci curvature tensor actually shows how a volume of matter changes when it moves from flat space to curved space. Metric tensor actually shows a way of measuring distance of all the causal structure of space-time. Riemann curvature tensors also describes curvature, and stress energy momentum tensor actually shows the matter movement in space-time. So don't worry on what all those terms are. We will just quickly touch base all those tensors so that you can understand. So the volume, when it changes, Ricci curvature tensor measures that. Metric tensor, overall the causal structure of space-time. Riemann curvature tensor is a little bit complex, so we can leave that for the time being. I will make a video on that separately. And stress energy momentum is the matter that moves through space and time. First of all, let us quickly understand what is a Ricci curvature tensor. So geometrically, the Ricci curvature is the mathematical object, I would say, that controls the growth rate of the volume of metric balls in a manifold, or you can say that measures how shape is deformed. So the Ricci tensor represents a volume of space that differs from a volume in a Euclidean space. So let us take an example. We take this kind of a curve in a coordinate, and then we take a point, and you see this actually moves in this way, right? Then we take another point, and it moves in the same way, but just due to the curvature, it seems that they are joined asymptotically, but they are not. So two initial parallel geodesics, forget this term, we will deal with that. Two parallel lines will begin to deviate due to curved space-time. And in the presence of curvature, these geodesics starts to deviate and the space-time volume starts changing. So in GR, the Ricci tensor is basically represents volume changes due to gravitational tides, which we can cover a bit. So right now, it actually measures how a shape is deformed. Okay, so we can take this kind of a sphere, right? And you can see this line going, so the people in purple and brown and green, they eventually join somewhere. And we take another analogy, the same sphere, right? And then what we see is that if we draw those lines, right, they are pointing at some. So you see this sphere, and you see this volume is changing, right? It is shrinking, shrinking. Maybe it will come to a point or so. So this equation, which we showed you, the Einstein field equation, the ball shrinks in size as it moves, and this change is actually what is formed or what is formulated out of Ricci curvature tensor. So just understand this. So the ball shrinks the way as it moves along this sphere, and that shrinking or the change is denoted by Ricci curvature tensor. So next what we do is that we come to metric tensor, which is a little bit very important. So we will take a little bit time. Before going into that, I would say that if you take 3 points and we draw kind of a right angle triangle, then we can use this formula to denote what is called infinitesimal distance. I mean, so we are using Pythagoras, but we are using d in order to measure infinitesimal distance. There is a reason for that. So if you get this kind of a graph, and we get 2 points, and then there's a line which is moving, so all those d are actually the differential distances that we are measuring. We will soon come to this reason, because once we are moving on curved space, the minute, small, infinite changes are required. So for that we need the differential distance. Okay, so we get this kind of a rubber sheet where there's an arrow which is pointed out there, and we use the same Pythagoras' theorem. And when the rubber gets stretched now, I would like to tell you, I hope you can now understand, right? Because this stretching I have shown when the person was throwing the ball, right? And that is the covariance that we need, that whatever changes happen, I need to register. So if it changes, then this changes, and we can use this formula to get we can calculate the distances. And if it further changes, then this both s and x and y changes becomes bigger. That is, x increases to 2x and y increases to 2y. Just try to recollect the second photograph in my earlier, just a few minutes back, which I have shown, where the person is throwing the ball and the coordinate expands. Then we can use this. Right. Why I showed this? Because this expansion, we can use something which is called a mapping. We are trying to measure a kind of a line on a sphere like this. And what I do is that I magnify the sphere, okay, and I put this straight line, which is not yet stretched, over this, this, and this. And I get lines over here. Now this is a kind of a technique why I am using this, because this is the stretched one, this is the unstretched one. On the unstretched one, if we can use dx dy, that is, we are using differential calculus, then g11 and g12, which is the tensor, we can plug in the values to get the details. So we can compute distance between 2 points on a curved manifold. Now, if you're not aware about the word manifold, you can just tell it as a surface, because we will cover up manifold in another video. That is another fundamental concepts of GR. So what we have done, we have put in and we have patched the unstretched segment of sheet into the stretched one. Now what we do is that we get this kind of a weird quadratic equation. Don't worry on deciphering this. Now further we take this stretched line surface, which has got a stretched line, and once we get this kind of coordinates, right, and we get this kind of points, and we still get this one, and this is the equation. So here you see dx dy means that the lines are not perpendicular, they are not orthogonal to each other. And you remember just a few minutes back I've shown that the problem while measuring vectors are they're not orthogonal. So what we do is that we get the unstretched, forget about 10 what it means, we get the unstretched information using this formula, and then we can plug in those into these values and we get the stretching information. Stretching means how much the curvature is stretched, how much it is dense, how much it is light, all those stuff. Right. So we use the earlier technique, which if you want you can go back and you can just see this one. So we use the unstretched into the stretched one just to get these values, and we can put it further in order to calculate these values and get the stretching information. So far so good. This is actually what the metric tensor looks like, right? This is what the metric tensor actually looks like. So we get these values over there, and that is actually stored in a tensor. So we get those lines, and you see the arrows. So these are the stretching information, in which way, which direction the curvature is. So it shows that how much and in which direction the space-time is stretched. It is stored in tensor. Don't worry, these are actually the ranks of tensor, which you can ignore for the time being, rank 1 and rank 2. And metric tensor is a rank 4 tensor because it is 4 by 4, that is 16 non-linear partial differential equation. Why it is 4? Because we are measuring length, breadth, height and time. So all in all, you can understand now that this metric tensor is something which is storing the causal structure of space-time, where it is stretched, where it is dense, the angles, the movement, all those things. So metric tensor, just to tell you, is a symmetric tensor, so you can cancel out these values 1, 0, 0, 1, 0, 2, 2, 0, 0, 3, 3, and if you go on doing this, what you get is this: G mu nu equals to G nu mu. Mu nu are basically the indices for calculating dimensions of space and time, and here it is, it captures the causal structure of space and time. Right? So, but remember also one thing, that it is also used in differential geometry or something else. So if you search internet and you search metric tensor, in general, metric tensor means just measurement of distance. But you have to type metric tensor in general relativity, right? Because in the mathematical field of differential geometry, metric tensor calculates defining distance or angles, these are the things. But this is what is important in terms of GR. So it captures all the geometric and causal structure of space-time, being used to define notions such as time, distance, volume, curvature, angle, and anything. Okay, so next we come to what is called a stress-energy-momentum-tensor. This is important because it causes the curvature. So this is the tensor. This one shows the momentum density. Don't worry, we will soon learn the meaning. This part is also the momentum density. This is the energy density. This is the shear stress. This part is the pressure, and this is the momentum flux. Right? So in all, what we can tell is that this E equals to mc squared, the energy density, because of the sheer speed of light, will always find the position right at the beginning, which is the left hand side of the entire tensor form. So we can think what it is, what this tensor is all about. It is that every part of matter and energy, whatever we think, pure energy, rest mass, relativistic mass, these, that, everything is there. It is the house of all forms of matter that we can imagine, right? So quickly, these terms: energy density is the amount of energy stored in given system. Energy flux is the rate of transfer. Momentum density is momentum per unit volume. Momentum flux is the rate of change of momentum, and we have got the classical pressure formula and the shear stress, right? So these are just the meaning of the terms. Now just let us put it in a matrix so that we can understand this. So first we deal energy density, that is responsible for the space-time curvature. Why? Because energy, the place where it is dense, it causes a curvature. Pressure, I have just shown an icon compressing something. It also acts as a curvature of space-time, and because pressure is movement of matter, it is a kind of a flux, right? Open the window and the sunlight streaming in, there is a flux. So this flow of energy, flux, causes curvature. Momentum flow, energy and momentum are closely related. So momentum flow is mass times momentum by mass. So if you want to go back, I think I made a little bit of rush. Anyway, so these are the factors: energy density, energy flux, and pressure. When they plugged in together over here, energy plus momentum plus pressure plus stress, that actually causes the entire curvature of space-time. So what is responsible for causing the curvature? It is this stress, energy, momentum, because you can see all the energy are all stress stored over here. So this is the one. So the presence of matter is a summary, causes gravity. Mass density is also proportional to energy density. Mass density also contributes to gravity. Momentum is the transfer of energy, and gravitational effects are caused by energy density, momentum density, stress tensor, and all of these factors contributes to the curvature of space-time. So this is another important concept: what causes the curvature of space-time. So fundamental concept 5 is this one. Ricci and Riemann curvature tensor measures the curvature. The metric tensor covers the overall, the causal structure and length and distance, where it is stretched, how it is dense, etc. And stress energy momentum tensor is the source of space-time curvature, and it describes the matter content. Right? So this is the point number 5, the fifth fundamental concept. Now we come to the last fundamental concept, which is moving along the curvature, or the geodesics. Geodesic, geo means earth, so it is basically measurement of the earth, but I will take a certain simple analogies. So here is a flat surface, right, and there are 2 points. So how do we move? How do we move from one point to the other? We take a straight line, obviously. Now if you take a triangle which is also straight, flat, I mean to say we take 2 points, how will we move? We will also take a straight line. Now if we can get a kind of a thing like this, then how do we move? If 2 points are given, we move from here to here and things become a little bit graph. We take a curved line. So if we get a curvature like this and 2 points, how do we move? We take this part. So what I'm trying to tell you is this one. This is a very nice analogy which I have actually watched in one of the interviews of a famous Indian astrophysicist Amal Kumar Chaudhary, and he was being interviewed by one of his students, Dr. Shayan Kaur. Now what he told is very interesting. I would like to share. Now given a tram and its path, right, something like this. Now if you ask a mathematician, how will the tram move, or what is the path where it will go? So the mathematician will tell that yes, I can calculate simple f equals to ma, and if it is a second order differential, then you give me 2 initial conditions and I can calculate it, right? But ask a rickshaw puller or the tram driver that in which way it will move. The rickshaw puller will tell it will just take the path of the tram. And that is the basic essence of a geodesic. So geodesics are simply the shortest part between 2 points. I remember this famous analogy. So asking a rickshaw puller, it will say that geodesics actually, if the tram will take the path, simple, the way the path is laid down. So what we can say is that in general relativity, geodesic generalizes the notion of a straight line to a curved space-time, right? Why? Because the straight line is no more straight. We are taking curved space, so it gets generalized. We don't call straight line, we call geodesic. So the world line of a particle from all external non-gravitational forces is a particular type of geodesics. So in general relativity, now here it is something what I would like to show that this gravity is due to the curved space-time. That is why geodesic is important. So in general relativity, the gravity can be regarded not as a force, remember, because we eliminated the concept of force in the Bern office of Switzerland, where Einstein told that, yeah, it is the same, the gravitational force, acceleration, inertia, it is the same. So it is due to the curved space-time, right? It's not a force, but a consequence of the space-time geometry. But the source of curvature, now we need to find the source of curvature. What is the source of curvature? Stressenergymomentumtensor, right? So for example, the path of a planet orbiting a star is the projection of a geodesic of the curved 4-dimensional space-time geometry. So this is very, very important, which I would request to have a note on this. An object moves through space-time in a straight line, which we call geodesic, because we have generalized that notion. But if the space-time is curved, gravity, that means, is present. This it doesn't mean that in straight line gravity is not present. Here in this context, this line will follow the curvature and may change the direction. Like if you are moving on the surface of a sphere, for example, this will be a change in direction. This is an extremely important concept. So geodesics are basically the shortest part that anything will take. And this is the effect which we call it as gravity. Because gravity is this effect, that is this movement of the particle of the line along the curvature. Okay, so if we take this sphere again, and you see this one, right, with the people meeting over here, and then we take this one, just a kind demonstration, 2 points and this one, and in a sphere, this great circle is actually a geodesic. So again, it is the shortest path, right? between 2 points in a surface, and geodesics the trajectories of the moving bodies under the influence of gravity, and this is the curvature which is causing the gravity. Just a quick note, this is how the geodesic equation looks like. This part, the top part, is the rate of change of the object's velocity. This tau square part is the proper time, that is the time which is measured by the observer. This gamma minus gamma part, or the gamma part, is the Christoffel symbol. We will talk about Christoffel symbol later when we are learning separately about Riemann curvature tensor. But this has the value of how space-time coordinates are changing due to the space-time curvature. And this is where the Christoffel symbol satisfies. You can ignore it for the time being. That means for a straight line, if I get 2 points, this is called a straight line geodesic, and where the gravity is present, it causes the curvature. So that is why it takes curve, and that is why gravity is considered not to be a force. Very important concept about geodesic. Okay, so gravity here at the bottom is not really a force, but rather manifestation of the structure of space-time. Okay, now this is here a very important observation I would like to tell you, that we know the first laws of Newton's motion: an object and rest will remain at rest. We have learned it in our school days. So I can also tell that geodesic motion is simply a statement of Newton's first law, because it says that it is in an inertial frame of reference, the inertial objects remain at rest or in uniform motion in a straight line. Whereas here in a curved space, curvature of space-time means that on a larger distance scales, inertial objects will also follow the curved path, like for example the orbit of the moon around the earth. So inertial objects remains at rest or in uniform motion in a straight line. Right. So I just mentioned this, on larger distance scales, inertial objects will follow the curved paths like the orbit of the motion. So the last fundamental concept is that geodesics are generalization of the Euclidean straight line, right? And it is the shortest distance that a body travels between 2 points. Okay. Now, once we deal with those, so where do we stand now? So we started with the equivalence principle, gravity and inertial frame of reference. Then we started with the principle of general covariance, which tells that the laws of physics should co-vary. That means we will be able to measure them in a proper predictable way. So we moved then to the flat or to the curved space, and we faced problem. What were the problems? That the basis of the vector changes, whereas the normal vectors remains the same. So because the basis of the vector changes in the curved space and things we need to form in a covariant manner, we need tensors. And why tensors? Because the laws will be invariant. It will be easy for us to do the mathematical calculations. And then we moved into measuring curvature using those tensors, right? We need tensors to measure the curvature, which led to Einstein's field equations. And we learned a little bit about the components, not all, the Ricci, Riemann, and the metric. And we understood that the curvature is basically the effect of the stressenergymomentumtensor, and moving along geodesics at the 2 shortest points. This is a kind of I would say, not a summary, but a workflow or a thought flow. It would be better to say that it is a thought flow in which we started with the equivalence principle and ended moving around geodesics. Now, when we talk of geodesics, we can move around this way, right? Straight or parallel to each other. We can also move in this way, or we can also move in this way, right? These are the possible movements. The first one is called a flat curvature, right? Because it is straight, right, in this way. This one is a positive curvature because it tends to meet somewhere. The curvature is positive. It showed it in riccicurvature's tensor. And this is a negative curvature because it is diverging in certain ways. These types of curvature, or the geodesics, actually gives rise to differential manifold and what is called a differential geometry. Very, very important. And we are going to cover. Without that, we won't be able to understand the next aspect of fundamental concepts, which would lead to certain other areas. Let us see what we would cover in the next video. How the differential geometry is important, and it came in general relativity, positive, negative, and zero curvature. What is the manifold? What is the differential manifold? And Riemannian manifold, what is a Riemann curvature tensor exclusively, how general relativity predicts black holes, what is the singularity of a black hole, and is it that time travel around the black hole is possible or not. So these are the second bit, and then only we will be able to cover the fundamental concepts of general theory of relativity. So I will be soon posting these topics on a fresh new video. Okay, so what are the summary that we learned? We moved from special to general relativity. We went into what we call flat space to curved space. We learned the tensors and their usages, why we need them, because things are changing and it is to be invariant. Measuring the curvature, we have learned the different components and parts of Einstein's field equation, Ricci and metric tensor, the stressenergymomentumtensor, why it is important, how it causes curvature, and moving along the path which is the geodesics. So that's all. This is the first part of the fundamental concepts of GR, and I hope you have liked it. Please do subscribe, like, comment, and press the bell icon so that you get all the updates from Physics for Students. The next video will be the fundamental part 2, where all those concepts will be covered. I wish you a very happy weekend wherever you stay, and whatever you're doing, please learn more about mathematics and physics, because that is how you really grow, you shine, and you progress in life. This is Shonat signing off from Physics for Students, wishing you a great weekend ahead. Stay safe and stay happy. Bye.
Now, you can be a part of our team. You can send your scientific articles, essays, research papers, lesson plans on a particular subject of science. For further details, please write to us at editor@physicsforstudents.com. Stay safe and happy.